Hello and welcome. So today we are going to look at this k nearest neighbor, and this is again a simple algorithm to classify data, right? So let's suppose the first assumption that nearest neighbor have is that similar input will have the similar output. And let me talk about the classification rule, that how it classifies the data. So let's suppose that you have given test data, that is x, and you want to classify this data, that which label it belongs to. So we have given this two label, that is 0 and this cross, right? We have two label, and now we have this new data, test data, and we want to make the classification that at which label this test data belongs to. So according to the k nearest neighbor classification rule, what does it assume? That the similar input will have the similar output. So what does it do? That it takes the k nearest neighbor. So in this case we can take maybe the 4 nearest neighbor. So it may take 1 nearest neighbor, 2, 3, 4 k nearest neighbor. So in this case we have taken this k nearest neighbor, right? So these are the point that is near to this test data, right? So we have taken this 4k nearest neighbor, right? And what is going to look, and after that, taking this k nearest neighbor, we are going to see that there are 3 zeros and there are 1 x, and whichever is greater, that we are going to assign to our test data. So this test data is going to be classified as 0, right? In this case, so this is how the classification rule this is how we can classify using k nearest neighbor, right? So basically, what does it do? That how it is going to select this 4k nearest neighbor based on the distance, right? So whatever the nearest 4 training data point that is near to this test data point, that data point are going to be the nearest neighbor of this test data, right? So this here you see, if this calculating the distances, you can say the crucial point, or because this distance will have an effect when you will have the higher dimension. So that is why I am mentioning that this distance metric will have, and we have a lot of other way to calculate the distances, right? Like if I give you an example, then there is one way to calculate the distances using Euclidean distance, right? That we use the formula to calculate the distance, and we have the other methods to also calculate the distances. So considering this calculation of distance is crucial in the k nearest neighbor, the method you are using to calculate the distance is crucial in this k nearest neighbor. That will have some effect, right? So that is the one point, and the classification rule that I have already described you, that how it makes the classification. And so that is what the assumption it makes, that the similar input have the similar output, and the classification rule is that for a test input x, assign the most common label amongst its k most similar training input. So that I have already described you, right? Now how we can formally define it. So it's not important, but it's good to look at this. So let's suppose that this is set sx. So what is set sx? The data that belongs to this k nearest neighbor. So this set is sx, and let's call this d as a complete training data. So this is a complete set of training data that we are calling it as d, right? So let's look at that, how we can formally define this. So we can say that this sx is subset of this d, right? You can look at this. This is your d and this is your sx. So sx is subset of d, and for all x dash y dash. So what is this x dash y dash? Let me tell you that it belongs to d but doesn't belongs to sx. So all these points are the x dash y dash, right? They belongs to d but doesn't belongs to sx, right? Now what we are looking is that and also let me tell you that this x is your test data, that is here, right? And this x is again your test data, right? If this x dash will be here, somewhere here, right? That is not in sx, and this x dash will belong to sx. So this x dash will be somewhere here, right? Now what we are doing, let's look at this. We are calculating the distance between test data and the data that belongs to sx, and we are taking the maximum of it, right? And here what we are calculating is the distance between test data and the data that doesn't belongs to sx, right? And this distance should be greater than equal to the maximum of this distance, right? So what does it mean? That all the data that doesn't belongs to this k nearest neighbor should be furthest away from the maximum distance of the data that belongs to sx. I hope it makes sense, and this is how we can formally define. So what does it mean? That every point in d but not in f, sx is at least as far away from f as the furthest point in sx. So the meaning of this, right? So now what we have done is that we have looked at the distance. Now we are going to make the classification, right? So our classifier should have a capacity that it should look at the most occurrence label, right? So in this case, the 0 has the occurrence 3 and this cross has the occurrence 1. So how we can define our classifier hx as a function returning the most common label of sx. So this is how we can define our hx. So So this hx is the mod of this. That means here mod is the means to select the level to the highest occurrence. So this is how we can mathematically define this k nearest neighbor problem. But that is what. Okay. Now you see that we have the here what we are calculating to find this k nearest neighbor is the distance, right? So in k nearest neighbor, generally we use a very general definition for the distance calculation that we call it the Minkowski distance, right? So this formula is the generalized distance formula, right? If you take p is equals to 2, then what you are going to get is the Euclidean distance, right? And if you take p is equals to 1, then it will be simple distance between 2 points by taking the difference, right? So since k nearest neighbor classifier fundamentally relies on the distance matrix, the better the matrix reflects level similarity, the better the classified will be. So this distance calculation should be taken into the consideration because it depends on the problem that what kind of distance we are going to calculate, right? So that is what it is written here, that the better the matrix reflects level similarity, the better the classified will be, right? So this is what the Minkowski distance, that is generalized form of the you can say the distance. And this KNN suffers from one problem, that is if you increase the dimension of your data set, then this KNN is going to fail, right? That is what we call it the curse of the dimensionality. So basically I'm not going to emphasize too much on this point, but what you can take from here is that if you want to calculate the distance between 2 points, then what happens if you increase your dimension, then it will have the effect on the distance between these 2 points. So if you are going to increase your dimension, then these 2 points going to be never to be, these 2 points will never be close to each other, right? So here what we are losing is the similarity that we use to calculate the k nearest neighbor, right? So the overall point is that if you increase the dimension, you will lose the so let me tell you one more time. If you increase the dimension, the 2 points is never going to be close together, right? So here what we are using is the distance formula to calculate the distance to calculate the k nearest neighbor, right? And if we increase the dimension, and what we are saying that if we are increasing in high dimension, if we have increased, or if you have the data points with high dimension, then 2 points will never be close to each other, right? So the KNN classifier makes the assumption that the similar point shares the similar level. That is what we have made the assumption. Unfortunately, in high dimension space, points that are drawn from the probability distribution tends to never be close together. So one way to understand is that if you are here, we have 2 dimensional data, and if you calculate the distance between these 2 points, it will be root over of x square plus y square, right? And this is, here we have introduced one more dimension, right? So this is 3 dimension, and if you calculate the distance between these 2 points, it is going to be x square plus y square plus z square, right? So you see that here the distance is greater than this distance, right? So it may happen that if you add more dimension to this, then the distance between these 2 points going to increase. So so we can say that these 2 points will never be tend to close together. And how it is going to affect in the KNN, k nearest neighbor, let me tell you that. So let's suppose you have this test data point, right? And in high dimension, what have happened that most of the point will be far away from this test point, right? And it will be too far that if you calculate the distance between the k nearest neighbor, that distance is going to have no meaning, or you can say it will have approximately same distance, right? So I'm not going to make too much point, or the takeaway point is from here. If you increase the dimension due to curse of the dimensionality, the KN will break down and it will not work as it was working in the low dimension, right? Okay. So at the end, KNN is a simple and effective classifier if distances reflect a semantically meaningful notion to dissimilarity, right? As n tends to infinity, KNN becomes very accurate but very slow. So if you have a lot of data points, the KNN will be accurate, but it will be very slow because it will be going to calculate to find the k nearest neighbor. It will have to do a lot of calculation to find k nearest neighbor point, right? And if dimension is large, points drawn from the probability distribution stop being similar to each other, and k nearest neighbor assumption breaks down. So that is all about the k nearest neighbor.